All right, so it is 10 o'clock, so we will get started. So let me just share my screen and we will jump right into it. Okay. All right. So what we worked on Friday was looking at sig figs. And I just want to reiterate, as we move on through the class, I'm always going to be taking sig figs into consideration when we do any problem that has to deal with math. So even like on exam 3 or exam 4, when you have a question, part of the grade of that question is going to be, did you follow the sig figs and did you get it right? So if you are still having problems with sig figs, we do have an SI session coming up on Tuesday and Wednesday. And also, you can email me and I'm sure I can find more practice for you. But what we're going to do right now is just a little more unit conversion, as that is something that students generally struggle with. And here we are going to be converting different types of volumes in A, B, and C. Then in D, we have one more just unit conversion problem to get everybody accustomed to that. So I'll do A, and then I'll allow you to, I'm going to ask you to try and do B and C before I give you the answer. All right. So I want to convert 27.8 liters to cubic centimeters, knowing that 1 liter is 1,000 cubic centimeters. All right. So when I do this, this one's actually fairly easy. So I'll do A and then B because I actually wanted to do something a little more difficult. So 27.8 liters. And I want to convert to cubic centimeters. So I set up my train track. Remember, what I start with always, well, almost always goes into the top bracket of the train track. I have liters at the top. I want to cancel that out, so I need to put a liters on the bottom. And then I want to end up in cubic centimeters. So cubic centimeters goes up at the top there. All right, so if I just look at my units, and this is a good way to practice unit conversion, before you do any numbers, just put your units in and see if your units make sense. So right now, my liters are canceling, and my final unit is cubic centimeters, which is what I want. So I put in 1 liter at the bottom, 1,000 cubic centimeters at the top, and then you just do your multiplication. You take everything at the top, multiply it together, divided by everything at the bottom, and this is 27.8 times 10 to the 3 cubic centimeters. So if you want to put all those zeros, that's okay as well. I just left it in scientific notation because it's super easy. When you have thousands, you can just put 10 to the 3 like that. So for those of you who wasn't quite sure what I did there, 1,000 equals times 10 to the 3rd. So it's just an easy way to keep track of numbers. So that conversion is relatively simple. Let's do B, because that's a little more complicated than you would think. So I want to take meters squared to kilometers squared. And my conversion for this is that there are 1,000 meters in 1 kilometer. All right, so I start with my 115 meters squared. All right. Now, why I say this is a little complicated is because meters squared are not the same thing as meters. You can think meters squared as meters times meters. That's what meters squared actually means. Kilometer squared is kilometers times kilometers, right? So I have a meter squared here, and my conversion is just 1 meter to 1,000 meters to 1 kilometer. So I'm just going to do my units. I'm not going to worry about numbers. Let's just do units. So meters at the bottom, because I have a meter squared at the top, kilometers at the top. All right. So when I do this, I have 1 meter, but remember, meter squared is meters times meters. So in essence, I only cancel out one of those meters, right? Right now, my units are meters times kilometers at the top. Because again, meter squared is just meters times meters. Having only 1 meter at the bottom only cancels out one of those meters. So I need to do the whole conversion again. I need another meters at the bottom, another kilometers at the top. So meter on the bottom, meter at the top, that cancels out. My units left over are kilometers times kilometers, which are kilometers squared, which is what I want my answer in. So now I can just put down the numbers, 1,000 to 1, 1,000 to 1. And when you are dividing, so at the top here, I said 1,000 equals times 10 to the minus, or to the third. If it's on the bottom, that's actually times 10 to the minus third. So this is 115 times 10 to the minus 6. So when you have multiple of thousands, they are additive in kilometers squared. If you're not comfortable with scientific notation, feel free to just punch in your calculator and write it down what it says. That's totally fine with me too. But yeah, so that's how you do a conversion of units that are like squared or cubic. For example, cubic feet or something like that. All right, so with A and B done, hopefully that's enough of an example for you to do C. And if you have C done, go ahead and do D. I will allow or give people a few minutes to do that on your own. See if you got it. If not, let me know any questions you might have. So the times 10 to the minus 6 is when you divide a number by 1,000, you can just do like 115 divided by 1,000. In scientific notation, you can just put 115 times 10 to the minus 3 if you wanted to. It's just a quick way to deal with thousands. So if I do 115, divided by 1,000 times 1,000, then you just do that minus 3 twice, and it's 115 times 10 to the minus 6. Or like I said, just put in your calculator if that's easier. Either way. And I'll give you the conversion. I forgot to do that. 1 meter is 100 centimeters. There are 100 centimeters in a meter. Centi means 100. Centennial, that's when you celebrate 100 years. A century is 100 years. So you can see where that word's coming from, centi, century, and all that good stuff. Kind of like a decimal or a decameter. There's 10 decameters in a meter. Goes along with the word decade. So once you actually get these prefixes down, you can start seeing how they're used in different applications. And if you're totally confused and not sure where to begin, please do let me know, because that's what this time's for. So if you're just sitting there waiting for me to give you the answer and not actively working, that is not a good use of your time. Or if you have an answer and you're not sure, just let me know through a chat and I can let you know if it's right or not. Remember, you can always message me privately too if you don't want to share your message with everybody. Okay, looks like we are getting some answers in for C. So I think everybody, so a lot of you just messaged me right now. If you message me privately, I don't see anyone that's wrong so far. So everybody should be right. So let me just do that really quick here. So 195 meters squared. For every 1 meter, there's 100 centimeters. But I have to do that twice because of the squared. 1 meter, 100 centimeters. So that is 1,950,000 centimeters squared, or 195 times 10 to the fourth, or I saw other people do 19.5 times 10 to the fifth, or 1.95 times 10 to the sixth. All those numbers are equivalent. They're all fine. And one more thing I forgot to mention, when giving an answer in this class, you must always have units. That's something else I'll be grading for. So if you did all the math right, but you don't tell me what units the number are in science, that's really bad because a number without units is meaningless for the most part. So just make sure you always have your units for your answers as well. Yep. Okay. So that's C. So D, let's see if we can do one more unit conversion for D, and then we'll move on to the lecture I have prepared for today, where we actually get into some chemistry almost, minor chemistry. Yes, for the way that train track methods work, you take everything on the top, multiply it, and so I'll repeat the question. We always multiply everything on top and divide by bottom. So yeah, you take everything on the top and you multiply it together, and then you take that number and you divide it by anything that's on the bottom. So for D, one thing I always find helpful for doing word problems is pictures. I'm a big picture person, so I like to draw pictures. So I have a runner, and you can see I'm an awesome drawer. Let's put some muscles there, a little hair. Okay, so this person wants to run 10 kilometers. And she can run 7.5 miles for every 1 hour. That's what miles per hour mean. I can go that far per 1 hour, right? If that's the case, how many minutes does it take to go 10 kilometers if 1 kilometer is 0.621 miles? So this will take a couple conversions. So you have to convert kilometers to miles and then hours to minutes. So this is a multi-conversion problem, which is what we'll see quite a bit of in this class. And hopefully this problem's not that intimidating since, you know, these are non-chemistry terms. These are just terms everyone should be familiar with, miles per hour and such. Maybe not running so much because, let's be honest, running is not fun unless you enjoy it for some reason. That's your thing, good. I'm glad you have a healthy hobby. Remember, the way to always start the train tracks, I always start with what we're given. So I want to run 10 kilometers. There are actually different ways to do this, but I find this one to be the most logical. Right, so I want to run 10 kilometers. And I know I don't want to be in kilometers because my speed is in miles per hour. So I'd rather be in miles. 1 kilometer is 0.621 miles. Right? Now, what is my speed? So right now my unit are in, the unit I'm in right now are miles because kilometers at the top, kilometers on the bottom canceled out. I don't want to be in miles though. I want to be in a unit of time, ultimately minutes. I do have a conversion though that says for every 7.5 miles, that is equal to 1 hour. So that is how I can convert between a distance and a time using my miles per hour. So for every 7.5 miles I run, that takes 1 hour. So my miles have canceled out and I'm now in a unit of hours. But I don't want to be in a unit of hours. I want to be a unit of minutes. So hours at the top, I want to put hours on the bottom and put minutes at the top because that's the unit I want to be in. And our conversion is 1 hour every 60 minutes. Hours cancel out. Now you take everything at the top, multiply that together, divided by the bottom there. So when we do that, if I did my math right, we should get a time of 49.68 minutes. Yes, it is 50 minutes. So 49.68 minutes. Now we have to check our sig figs. So if we go back in the in our unit conversion here, we have 10.00, that has 3 sig figs. 0.621 has 3 sig figs. This 1 hour, that's not like, that's actually like an infinite. When you say like miles per hour, you're gonna assume that hour is an exact measurement. So the sig figs for like that is infinity. So anything like miles per hour that hour on the bottom will be infinity because it's 1 exactly. 60 minutes is also infinity. It's 60.000000000. So anything that's like a direct conversion, like 1 liter to 1,000 centimeters, they have infinite sig figs. That's an exact number that you're sure of to infinity. You know it's 1, right? So right now, the amount of sig figs we have are 3. Let's look at the bottom. So 1 kilometer, infinity. 7.5 to sig figs. 1 hour, again, infinity, because 1 hour to 60 minutes, of course. So my answer should have 2 sig figs. So my first 2 numbers are the significant one. So I have 49.68. Going to round up because that's a 6. That's 50 minutes. Okay. So any questions about that before we move on to a little bit of chemistry? Why is it 2 sig figs again? Because if you look here, 10 kilometers, 3 sig figs, 7.5, 2 sig figs, 0.621, 3 sig figs. Everything else has infinity sig figs because like this 1 kilometer is 1.00000 all the way to infinity. You're going to assume that 1 kilometer is measured exactly. So when you do multiplication, you always go with the number of the lowest amount of sig figs. In this case, it's 2 from that 7.5. Because I can't assume that 7.5000000 infinity. Okay, so we will move on then to what we're going over today. So I'm gonna clear all my scribblings here like a madman. And again, all these answers will go up in case you didn't have time to write it down. Don't worry. So stop share, new share. We want to go to the last day of August. It's almost September, yet it's still going to be 100 degrees out. Yay, Texas. At least there's no snow. That's all I care about. So from beginning, okay. So Monday, August 31st, we're going to talk a little bit of chemistry. And we're going to talk about the 3 laws that make up like the basics of chemistry and chemical theory. And first, we're just going to start with the idea of atomic theory, in that everything you can see is made out of atoms. And we know that because of 3 laws discovered, or postulated rather, hundreds of years ago now. And the first one is the law of conservation of mass in 1789 by, and I apologize to anyone who speaks French, I'm going to butcher this guy's name, Antoine Lavoisier. He's a big player in chemistry. The more you study chemistry, the more you see his name pop up on. And he said that in a chemical reaction, matter is neither created nor destroyed. And the way he set this up is actually a cool little experiment. So you don't have to memorize this, but I just think it's neat. Basically, he grew like a little plant in the dirt and then kept that like in a dome. And like he measured it before the experiment started, and then he measured it at the end of the experiment, and a plant grew, but the mass never changed. So in his experiment there, he saw, oh, no matter what's happening, the amount of mass is not changing in my system. So you can't create or destroy matter. And we later learned, because of Einstein equals mc squared, energy equals mass times the speed of light squared. You can change mass into light. It just takes a lot of energy, but it is possible. So you can't create or destroy matter. It can only change forms, right? So that's our first law of conservation of mass. There we go. So we do have some problems go with this. So let's say I have a hydrogen-filled balloon and it has 1.5 grams of hydrogen. And when I light it on fire, it reacts with 12 grams of oxygen. If water vapor is created, and water vapor is the only thing that I make, how many grams of water vapor will I form? And this problem, do not overthink it. I'm guessing you should be able to get in like 10 seconds. Remember, matter cannot be created or destroyed. So if I have 1.5 grams of hydrogen and I ignite it with 12 grams of oxygen, and I only create water vapor, that mass of the water vapor is, drum roll please, 1.5 plus 12, you make 13.5 grams of water vapor because it can't be created or destroyed, right? Let's take a look at our sig figs because I forgot to do that there. So here, addition and subtraction, when you're looking at sig figs, remember you're looking at the decimals. So 12 has one number, one digit after the decimal. 50 has 2. You always go with the number of the smallest digits, so that's why it's 13.5. All right, next one. Maybe now that you saw A, you can get this one in like 5 seconds. I have a gas tank, 21 kilograms of gas. I burn it. I use 84 kilograms of oxygen. How much carbon dioxide and water are produced? What is the mass? And in a combustion reaction, for the most part, the only thing you make are carbon dioxide and water. Those are your two products. So I take 21 kilograms of gasoline. I add that to 84 kilograms of oxygen. You make 105 kilograms of water and carbon dioxide. So, don't you wish all the math in this class was this easy? Unfortunately not. But that is the law of conservation of mass. What goes in must come out. The weight of your reactants must equal the weight of your products, unless you have reactants left over. You cannot create new mass. You can't destroy it. All the mass we have in the universe is fixed. No more is ever going to be produced, and you can't destroy it. You can only turn it into energy. Or like the atomic bomb, that's what you're doing. You're taking uranium and you're turning it into energy. Anyways, so that's the first law, conservation of mass. Law 2 is a little weirder. It's the law of law 2 is actually not weird. I'm thinking law 3. But law 2 is the law of definite proportions. And this was Joseph Proust, 1797. If you got a sample of an element, no matter where you get this sample from, it will always have the same proportion of their constituent elements. So for example, I have water. If I take water from my tap here in San Antonio, or go up to Michigan and get water from Lake Michigan, or go over to Europe from the Baltic Sea and get water, no matter where I get it from, it will always have 2 hydrogens per 1 oxygen, or 16 grams of oxygen per 2 grams of hydrogen. No matter either way I measure it. All water always has this ratio. It will never change for water. That is the law of definite proportions. Okay. What about heavy water? Those of you who don't know what heavy water is when you have a deuterium instead of a hydrogen. So it has 2 protons instead of 1 proton. And so there the mass doesn't work out. But the law of you always have 2 hydrogens to 1 oxygen is true, because deuterium is still a hydrogen. It just has an extra proton, extra neutron, not proton, extra neutron. So it's still a hydrogen atom. So they didn't know like really what atoms were at the time. So Proust couldn't really say that, but the law still holds up. You'll always have 2 hydrogen atoms for 1 oxygen, or it's not water. Okay, so let's take a look at our example problems here. We have 2 samples of carbon tetrachloride, and we break those down into carbon and chloride. 1 sample will give you 38.9 grams of carbon and 448 grams of chlorine. And the other sample produces 14.8 grams of carbon and 134 grams of chlorine. Did we follow the law of definite proportions in this problem? So I will work out this one because it might not be really clear where we're going with this. And then I'll let you do B just so you can get the hang of it. Okay, so when you do the law of definite proportions, you're doing ratios. Really, you're asking, what is the ratio? Let me get my pen here. What is the ratio of carbon to chlorine, right? And generally, when you're in the lab setting, you can't really count atoms easily, so you have to measure it. So here we're given masses. So in sample 1, so I'm gonna call that S1, I have 38.9 grams of chlorine or carbon for 448 grams of chlorine. So I take those 2 numbers and I divide them. And my ratio is 0.0868. All right. Now, if the law of definite proportions is true, my other sample of carbon tetrachloride should have the same ratio. So let's take a look. So my sample 2, I have 14.8 grams of carbon for 134 grams of chlorine. Okay, so when you do that, you get 0.400, I believe. So you get 2 different numbers, which is bad. Well, bad in that we just broke a law of chemistry. So explain your answer. What is the simplest answer for this being different? Does anyone want to give a guess other than the answer of I changed the numbers? If you were given a real experiment and your numbers were this far off and you were given 2 beakers that said these were carbon tetrachloride, and then you did this experiment and you found, wait, the law of definite proportions is not being followed, what would you assume? What would be your explanation? It does not matter. So so the question is, I thought we put the bigger number on top. It does not matter which one you put on top and which one you put on bottom, as long as you're consistent. You can put both having big numbers on top and both small numbers on the bottom. Does not matter anyway. So I got a different answer for S2. Let me just calculate that again, because I might have put in a 9 instead of a 4 on my calculator. 14.8 divided by 134. Oh yeah, it is. I don't know what I did with my calculator. So that's, yeah, that answer is way different. 0.110. Yeah, so somebody said that an explanation was they are not consistent with their proportions. That answer sounds a little vague to me, as in I'm not quite sure what that means. The simplest answer, as given by Maria, is 1 sample is not carbon tetrachloride, right? So we're going to assume we live in this universe, and if somebody hands you 2 samples of carbon tetrachloride, carbon tetrachloride, you can't just look at it and be like, yeah, I know for sure that is or isn't. So if you do this type of experiment and you see the ratios are different, well, the simplest answer is one sample is not carbon tetrachloride because they should have the same amount, right? So with that for A, try to do B and see, does that follow the law of definite proportions? Do we have 2 samples of magnesium fluoride here? Oh, I see why that was a 4. It's because my handwriting's horrible. It is 2 1s. Oh, sorry. B is a little bit different. I just read it again. B, you are going to assume definite proportions are in effect. And I'm asking you how many fluorines are in your second sample. Apologize there. So again, the way that I would start this is with any word problem, write down a simpler version of what's going on so I don't have to look at all these words again. So sample 1, I get 1.65 kilograms of magnesium for every 2.57 kilograms of fluorine. Now, second sample, we are going to say that this is magnesium fluoride. And you have sample 2, 1.32 kilograms of magnesium. And the question is, how many grams of fluorine? So the way I would tackle this is just like how we did above. So I'm going to actually do it up here above the problem 2 to give myself some more space. So first sample, I'm going to take my magnesium, 1.65, divided by 2.57. So that's my fluorine. So magnesium on the top, fluorine on the bottom. Divide those two numbers, and you get, just double check, 0.642. That is my ratio between magnesium and fluoride for sample 1. Sample 2. All right, so I know in sample 2, I got 1.32 kilograms of magnesium. I don't know how much fluorine I have, so that's an X. But I do know that for magnesium fluoride, when I divide the two, I get 0.642 from sample 1, right? So now I need to solve for X. So those of you who do not remember how to do algebra, what you do, you take X, multiply each side by X, and you get 1.32 equals 0.642X. Divide each side by 0.642, and you will get X equals 2.05 kilograms of fluorine. So that is how we can use the law of definite proportions to predict how much weight of an element we'll get from a compound. Again, I'll just double check my math there. Actually, it should be 2.06. 2.06. Yep, 2.06. So any questions about the law of definite proportions before we get to the weird one, the weirder one, I should say? Okay, let me clear all my scribbling. Go on to the law of multiple proportions, 1804 by John Dalton. Again, Dalton's one of these people who, the more you study chemistry, the more his name is popped up. The weight of an atom is named after him. We call that the Dalton. So he's another heavy hitter in chemistry. And what he said is that you have two elements, and we'll call that element A and element B. And when you form two different compounds with these elements, if you combine element B with 1 gram of A, and you get two different compounds, you'll get a ratio of small whole numbers. I know, that's like super confusing, right? So what does that actually mean? So you have one atom of A. It will always combine with 1 or 2 or 3 or more atoms in B. Basically, in a nutshell, he's saying that you can never have half an atom in an element. Your compounds would always be like AB, AB2, AB3. So when you look at the masses of B in these compounds, the ratio in different compounds will always be whole numbers. Let me give you an example. Maybe that will make this clearer. Okay, so we have carbon dioxide. Carbon dioxide is CO2, right? So when we measure CO2, we have 32 grams of oxygen for every 12 grams of carbon. And let's take that ratio. Let's take 32 divided by 12. So I'm taking the ratio of oxygen to carbon, and my ratio is I have 2.61 grams of oxygen for every 1 gram of carbon. Now let's take another compound that's made out of carbon and oxygen only, and let's take carbon monoxide. Now that's just carbon and oxygen. For carbon monoxide, I have 16 grams of oxygen for every 12 grams of carbon. Again, take the oxygen to carbon ratio. So I take 16 divided by 12. And for carbon monoxide, I have 1.33 grams of oxygen for every 1 gram of carbon. Now, this is where the law of multiple proportions comes in. You have one element that's always at 1 gram. It has to be the same element. So here, if we're looking at carbon dioxide and carbon monoxide, our element is carbon. So in both cases, we set that at 1. Then we take our oxygen amounts and we divide them by each other. So I take 2.61 divided by 1.33. Here, you do want to put the bigger number on top. And what the law of multiple proportions says is that when you divide these two numbers, you will always get a whole number, 1, 2, or 3, or 4, or 5, etc., etc. Now, when you do this math, you don't get an exact whole number. So you get 2.61 divided by 1.33. You get 1.96, but that's generally close enough to 2. The reason why it's not exactly 2 is because of isotopes, which we're not going to get into right now. But if you get like 1.9 something, 2.9 something, 3.01, 3.05, that's close enough to a whole number that we're going to count it. But that is the law of multiple proportions. That is probably the most obtuse, the most difficult to get. So we're going to do practice problems on that, just so we're all clear on what this law says. All right. So I have two different compounds containing osmium. So osmium, that's a weird element. Osmium has the symbol of OS and oxygen. And they have the masses of oxygen per gram of osmium. So what we're saying, in compound 1, we have 0.168 grams of osmium for every 1 gram of oxygen. And in compound 2, oh, sorry, I got it the other way around. It's 0.168 grams of oxygen per 1 gram of osmium. Compound 2, we have 0.3369 grams of oxygen per 1 gram of osmium. And we're asking, is this consistent with the law of multiple proportions? So we look at our setup, right? And we already have one compound that's already 1 gram. So we just divide the other compounds by each other. That should be a whole number. So we take 0.3369. We divide that by 0.168. And you get 2.005, which is close enough, which is basically 2. So yes, these two compounds are consistent with the law of multiple proportions. Yeah, 2.005. So just round the 2 when you're that close to a whole number. So for the last couple minutes, I have B here for you, and I believe that's our last slide. Not quite. Okay, but we'll end here. So B, we have the element palladium, and we're forming 3 different compounds with sulfur. So in the table, your table are grams of sulfur, and it's always 1 gram of palladium. I want you to show me, are the combinations of A and B consistent with this law of multiple proportions? Are B and C, and are A and C? So just confirm or not confirm that these compounds are consistent with the law of multiple proportions, and that is where we will call it today. So we have a yes vote for A and B. What's on C? C is 0.151. So if I do A to B, right, 0.603 divided by 0.301, that is roughly 2. So yeah, A and B checks out. Let's do B to C. So I'm going to take B, 0.301 divided by 0.151. That roughly equals 2. So that checks out. Let's do A to C. A is 0.603. C is 0.151. Take these two, divide them together. That should be roughly 4. Yeah, that checks out. It doesn't have to be 2. As long as it's a whole number. It can be 1, 2, 3, 4, 5, a million. It probably won't be a million because of chemistry, but that's the idea. When you when you have different compounds made out of the same elements, if you take one of those elements and always make it 1 gram, and you compare the weights of the elements to each other and do a ratio like we did, it will always be a whole number. That is the law of multiple proportions. So that is the end of our time today. If you have any questions, as always, please do email me. Like always, I will put up a homework in Mastering Chemistry. Do be aware there are 3 parts, so I'll put up one after today, one Wednesday, one Friday. And hope everybody has a good day. I will put this video up. See everybody hopefully on Wednesday. Take care.